Okay, this is Arun Srinivasa again. This one, we are now getting into quantifying force intensity. I described last time what force intensity means. Now we are going to quantify it. Many of you are aware of it. I'm thinking that this will be a fairly quick survey of this. But there are a couple of important points. One has to do with being very careful about what we mean and how this is computed. I'm sure you're familiar with it, but you're somewhat sloppy maybe. Okay, so let's go and try and see if we can do that. Okay, so let's look at a particular example. So we are going to compute average force intensity given the forces. So there is a net force acting on the top surface of a body whose area is 10 millimeters squared, and the force is 100 newtons. That's the magnitude of the force. It acts at 0 degrees to the y-axis. That's the direction of the force. What is the average stress or traction vector on the surface? So let's see what kind of problem we're talking about here. There it is. Right? So first of all, notice that I've shown only one force. As long as you know the force on a surface area, it doesn't have to satisfy equilibrium or anything. It just requires you to know something about forces. Okay, so average force, and our procedure is always the same. Choose an axis. Write the force vectors in terms of our chosen coordinate system. In our case, our force vector is 100 J newtons. Compute the average force intensity vector by dividing by area, and then report it. That's all. So we compute F over A. Please remember, notice that the result is a vector. It says 10J because area is 10, F is 100, so 100 over 10 is 10, and then the direction is J. So the traction vector or the force intensity vector on that surface is 10J megapascals. Okay, now notice the notation of this. Whenever we write traction vector, we don't just write T, we always indicate on which surface it is acting by telling you which is the normal. So now, right now, this says T sub Y. Y means it is acting on the face that is perpendicular to the Y-axis. Can you see that? And to not confuse it with components, where we also write like this, Vx, Vy, Vz, that kind of thing, we always put that in bracket so that it's easy to see. And if it is not confusing, then we won't, but typically we will put that in a bracket. Okay, so please remember, that's how it is referred to. Okay, so key takeaways here. There is no need for the object to be in equilibrium to find the stress, as long as I know the forces. For a given surface, it is a vector on that surface. So you should never talk about stresses as scalars. They are vectors on given surfaces. Whenever we write them, we always indicate the surface normal. Okay, that's what tells us which surface we are talking about. Okay. Now, let's try a different problem just to drive home this point. So now we have a net force acting on the top surface on an area A equal to 10 millimeters squared. Is again 100 newtons. It acts at 30 degrees to the x-axis in the xy plane. So this angle between these two lines is 30 degrees. What is the average force intensity or stress or traction vector on the surface? We know the procedure, right? Choose the axis, compute force components in terms of the axis, find force component intensity, and then report it. Okay. Now, what I want you to do is don't just follow, pause the video and you try it. You cannot build muscles by watching an exercise video. So the more problems I solve, I get better, but I want you to get better. So your task should be to solve this and then compare with what I have. So what I had was this. The force is 50I plus 86.6 J. 50 is, so is cos 60 degrees. It should have been acts 30 degrees to the y-axis, not to the x-axis. I'm sorry. So it's 50I plus 86.6 J. It's cosine 30 and sine 30. That's what the force is. And I'm sure you know how to do that. The area is, again, just 100, is just 10 millimeters squared. So force over area is given by 5I plus 8.66 J Newton per millimeter squared, or 5I plus 8.66 J MPa. So I want you to understand that traction vectors, force vectors are always vectors. So the phase indicator is the same as before, but because the force was different, the net traction vector was different. Okay. If the force changes magnitude or direction, then the traction vector will change. Okay. Now let's look at a different one. This time, we are going to look at a surface which is tilted at an angle of 15 degrees to the y-axis. So procedure is the same. Choose the axis, compute the force component in terms of the axis. Now we have one additional step. We have to find this yellow colored area, how much that is compared to the blue color area. If blue colored area is given as 10 millimeters squared, what's the yellow colored area? And then force over area, that's all. You don't have to do anything else. So you try your hand at it and then come and look at my answer. Okay. So let's see if we can get it. Okay. So for the first problem, it's very easy. 120 newtons divided by 10 millimeters squared, because I already know the area. F over A is Ty, and there is 12J. Because force is 120 newtons, area is 10 millimeters squared. That's what it is. You got that? That's easy. Now let's look at the second case. First thing to do is area is now 10 over cos 15. Okay. So the traction vector is force divided by area. So 120J divided by 10 over cos 15. It is 10 cos 15J MPa. I want you to understand something. All you have to do is find the area. That's all. The force vector will always be the direction of the traction vector will be the direction of the force. The only reason for looking at what exactly surface does is to figure out which way how much is the area. That's all we are interested in. Okay. So I hope you got that idea. We are done. We already, and by the way, notice the notation. The subscript n refers to the normal to the surface in question. That is how we tell them that these two are different things. This is Ty, this is Tn. Ty means normal was y direction. Tn means normal was this n direction. And you have to separately list that n. Okay. If you have questions about this, you can ask me during class. But this is all there is about actually doing the fundamentals of what is meant by force intensity. Okay, thank you very much. We are done.